We have a 4 kilogram mass, 10 kilogram mass, connected by a strong but massless rod, or at least a rod of negligible mass, rotating about the center of mass. In other words, if I was to throw this thing, it would rotate about its center of mass. Okay, so this is rotating about its center of mass one way or another, whether I throw it and rotate it, or whether we constrain it to rotate about that center of mass. Doing so, of course, keeps everything nicely balanced, to speak of it intuitively, and prevents the system from wobbling. So, the distance between these objects is 80 centimeters. Length of the rod is 80 centimeters. First, we want to calculate the position of the center of mass before we go much further. Now, I'm using a circled cm for center of mass. I should have used capitalized cm, but in the interest of time, I'm not going to do that. So anytime I've got a circled cm, that stands for center of mass, and any uncircled cm stands for centimeters. Okay, so to calculate the center of mass, well, if we think, and this is a small picture, and this is something we already know pretty much, but if we were to balance this system at some point along the rod, and if we were to, if it's in balance, then the sum of the torques exerted by the two weights, the forces of gravity on the two masses, are going to be equal and opposite. We'll have equal and opposite torques. Well, that immediately leads to the equation for the position of the center of mass, and we conclude that in this situation the center of mass occurs at 5/7 of the distance, 5/7 of the separation between the two objects. And since the separation here is 80 centimeters, the center of mass is going to occur at 5/7 of 80 centimeters. Okay, now what we want to do, and the reason we first have to calculate the center of mass is, now we want to calculate the moment of inertia of the system about the center of mass. So the moment of inertia is what? It's the mr squared for this and the mr squared for this. Now we assume these to be concentrated masses, ideally point masses. But we just add the mr squared for this to the mr squared for this. Okay, well, the r is our distance, our moment arm, our distance from the center of mass, which is 5/7 of 80 centimeters, so that this mass has a moment of inertia equal to 4 kilograms times 5/7 of 80 centimeters is 400/7 of a centimeter quantity squared. This distance from the center of mass to the 10 kilogram object is going to be the remaining 2/7 of the 80 centimeters, and that turns out to be 167th centimeter. There's a, let me pause here and just put a little line of demarcation here. This calculation of the center of mass was getting confused with this, and I just realized it here. My eye caught this, and I thought, well, that looks like part of this calculation, and it isn't, so I drew a line there. Okay, so anyhow, completing this calculation for the moment of inertia, we just square these quantities, we add them up, and we approximate the result, and we get something like 86.9 over 49 kilogram meters squared. Okay. Now, squaring 400 is, clearly 640,000. Square of 160 is 256,000. We add those up. We get 896,000. We convert the centimeters squared to meters squared. Well, a centimeter squared is 0.01 meters squared. 0.01 meters quantity squared, which is 10 to the negative 4th meters, giving us this result, and that's very straightforward. So, this is our moment of inertia. And I believe this is exact. I believe it's probably correct, but as always, check me. Okay, now the kinetic energy then of the system. Well, let's back up a second. What we're going to do with this system is, through some mechanism or another, maybe this rod just shrinks, this thing is going to contract to a length of 40 centimeters. And that's going to change its angular well, it's not going to change its angular momentum because there's no net torque on this system. We're contracting the system, meaning that the forces are being exerted along the line of the rod, which is perpendicular to the direction of motion of either of the masses. So there's no work done on anything by that contracting force. There's no work done in the direction of motion of either of these objects, or more properly, there's no torque exerted by those forces because those forces are exerted parallel to the moment arms. Okay, so what we want to do is we first want to calculate the kinetic energy of the system, and that's a straightforward calculation, 1/2 moment of inertia times the square of the angular velocity, which is given to be 40 radians per second, and we get about 750 joules. Okay, now we're going to contract the system. The angular momentum is going to remain constant, but the moment of inertia is going to become less. Well, if the moment of inertia becomes less, but the angular momentum stays the same, that means that the angular velocity has to increase by the same proportion by which the moment of inertia decreases. Well, at the 40 centimeter length, I'm asserting the moment of inertia, we'll call it I sub 2, is 1/4 the moment of inertia at the 80 centimeter radius. Now, why is that? Well, if we contract this to 40 centimeters, then both of these masses will be twice as close to the axis of rotation, to the center of mass, meaning that the R for each of these calculations will be half as great. So when we calculate the moment of inertia, we'll be multiplying by the square of half the distance in each case. So each of these distances will be half as great. And when we square something half as great, we get something 1/4 as great. So both of these moments of inertia, the individual moments of inertia, the moments of inertia of the individual masses, will be 1/4 as great, so the total moment of inertia will be 1/4 as great. Now we could go through and actually calculate, 5/7 of 40 centimeters and 2/7 of 40 centimeters and see that we get, 200 over 7 centimeters and 80 over 7 centimeters. Do the calculation, but we're assured that we're going to come out with something 1/4 as great, so we don't actually have to do that calculation. Okay, so the second moment of inertia is 1/4 as great. Since the angular momentum is constant, the product I omega is constant. If I becomes 1/4 as great, omega has to become 4 times as great. So the second angular momentum, or angular velocity, is 4 times the 40 radians per second. Now we could then calculate the kinetic energy of the system. It's got a 1/4 the moment of inertia. We have 4 times the angular velocity. The kinetic energy being 1/2 the product of moment of inertia with the squared angular velocity. Well, we have the moment of inertia, we have 1/4 that would tend to give us 1/4 the kinetic energy. However, the angular velocity is 4 times as great, and angular velocity gets squared, so you have 16 times the squared angular velocity. So 1/4 the moment of inertia and 16 times the squared angular velocity is going to give you 4 times the kinetic energy. Now I just said here the kinetic energy doubles, and I'm not sure what I'm thinking. It actually fourples, doesn't it? It quadruples. Okay, except in this class, of course, fourples really isn't a word, but it stands for quadruples. The kinetic energy quadruples. Now you might ask, where does the energy come from? Well, it's going to take some force to pull these things together because there's just a centripetal force tending to pull them apart. Okay, there's a centripetal force necessary to hold them in their circular paths. Okay, and you're going to be working against that centripetal force if you try to bring them closer together. Of course, that centripetal force is going to vary. It becomes an interesting problem to work out what happens as you contract this to the centripetal force and how that then integrates to give you the work you have to do to pull it in. But it turns out that that work is, in fact, identical to the change in the kinetic energy of the system. And that's an interesting problem to actually work out. I'm not going to do that one for you, but I'm going to toss that out as a nice, fairly challenging problem.